Okay, thanks, Mark, for the invitation to speak here today. Also, I'd like to take the opportunity of thanking the IAS for the unique opportunity given to us with this wonderful program. Many great people around, so thank you. So today, I'm going to talk about my work with André Neves on the variational theory of minimal surfaces. So I'll try to explain what has happened in the subject for the past few years, and I'll try to point to future research directions. So mostly, this is based on joint work with André Neves and some other collaborators who I will mention during the talk. Okay, so first of all, everything I'm going to say here concerns the area functional. So my setting is going to be that of n plus one dimensional Riemannian manifold. So let's say a closed Riemannian manifold. And then I want to look at the codimension 1 problem. So I will take sigma of dimension n contained in M. And this is going to be a closed hypersurface. So I would like to look at the area functional as a function defined on the space of closed hypersurfaces inside some Riemannian manifold. And of course, the critical points of the functional are called minimal hypersurfaces. So they can be characterized as being hypersurfaces with vanishing mean curvature. But of course, the variational definition basically says that if I compute the first derivative of the area functional over some variation of my surface, say t equals 0, this is 0 for any, say, ambient deformation. So for any flow diffeomorphisms starting with the identity. So I would like to study these hypersurfaces from the variational point of view. Okay, so of course, let me just say a few words about the one-dimensional problem. This is very important, of course, because in that case, minimal hypersurfaces are closed geodesics. And this situation is very special, of course, because closed geodesics also admit a dynamical interpretation, so they are periodic orbits of the geodesic flow. But of course, once we move to higher dimensions, we lose that interpretation, and then the main method will be calculus of variations. So, so I guess sort of like the subject started with a question of Poincaré, who asked whether any Riemannian sphere contains a closed geodesic. So if you ask this question for a torus, then it's easy because you can just pick a non-trivial homotope class, and then you can minimize the length in that class and get a non-trivial closed geodesic. But in a sphere, every closed curve is homotopic to a point, so that's not going to work. In Poincaré, I think he had some minimization schemes in mind for some particular situation, but it was Birkhoff, guys, 1920s, who realized that this is not a minimization problem, so he invented the Minimax technique. So let me explain his idea. Well, you have some Riemannian sphere, and then what he realized was that if I consider the space of loops inside that Riemannian sphere, and if I try to draw that space, it would look like this. So this would be the space of loops. So there's a trivial critical point here, which would correspond to point curves with length equal to 0. But if you want to detect a non-trivial critical point, what you do is you introduce this idea of sweep outs. So you take a one-parameter family of loops sweeping out a two-dimensional sphere in a non-trivial way. And if you draw, of course, for each curve like this, it corresponds a point here, the space of loops. So that particular one-parameter family would look something like this. So this is CT, say T01, and this would be, say, the curve C sub T. So in other words, the space of loops has non-trivial topology, and then what you can do is, for each such one-parameter sweep out, you compute the sup of the length functional, and then you minimize that, and by doing so, you actually approach the critical point. So you define this number L, it's in sort of minimax. So first you sup the length over this family, and then you minimize over all sweep outs. And one can see that this number is positive and is actually the length of some non-trivial closed geodesic. So the answer to Poincaré's question is yes, every Riemannian sphere contains a closed geodesic. You can do it this way. All right, so this work later inspired Morse and also Wolsternick, Schniremon. Inspired them to look at maybe higher critical points. So this is a critical point of index 1, but you can, of course, look at critical points of higher Morse index. And the basic idea, of course, is that, I mean, the structure of this set of critical points should be related to the topology of the underlying space. So in the early 90s, by combining the works of several people, so Bangert, Franks, also Hingston, one can prove that actually every Riemannian sphere contains infinitely many non-trivial closed geodesics. As far as I know, there's no completely variational proof of that theorem, because Franks was working from the point of view of dynamics. Okay, so this is the theorem in dimension 2, and what I would like to do is to consider then the higher dimensional problem. Okay, so I guess there have been constructions of closed. I'm always interested in closed minimal surfaces here. So there were constructions of closed minimal surfaces since, I guess, the early 80s. In fact, there is this so-called parametric approach, where you look at surfaces as given by maps from a fixed topological two-dimensional surface. So shall mention here work of Shen Yao on incompressible minimal surfaces, work of Sachs, Uhlenbeck to produce minimal spheres.
Fernando, let me
yes.
say, I think Bangert and Franks together proved it, but it was a mixture of Mach theory in certain cases and the other. But Nancy actually gave it completely Mach theory to prove.
Is that so, Nancy?
No, I think that's true.
Okay.
Yeah, okay. So Sachs Uhlenbeck for minimal spheres, and I like to mention here also Riviere, who lately has been revisiting the subject, and he'll be here in the spring. Could also mention Mick Simon Yao, also not much on the parametric approach, but also a method to construct closed minimal surfaces. So that very much uses dimension 2, because you take advantage of the existence of conformal parametrizations, so on, but that's, of course, a very established approach. So this is not the approach I'm going to take here. I'm going to look at flat cycles. So I don't care much about the parametrization. These are going to be surfaces by themselves. So of course, flat cycles are related to the flat topology. What is the flat topology? Well, you might imagine that two closed surfaces are very close to each other in the flat topology if the volume in between is very, very small. Okay, so a picture like this. So maybe a sphere could be very close to something with genus 1 because you can add a small handle here. And maybe there could be some spike. As long as sort of like this volume in between the surfaces is very, very small, there are going to be cycles very close to each other in the flat topology. And the definition is, well, you look at polyhedral surfaces, for instance, there's a notion of boundary, and then you complete that space with respect to the flat topology. So those are called flat cycles. And in fact, one can use flat cycles to define, as Birkhoff did in 2 dimensions, one parameter sweepouts. Have some Riemannian manifold, dimension n+1, compact, maybe some topology here. So I can talk about families of hypersurfaces, say sigma t. And I'm going to imagine that each sigma t is the boundary of a region, u sub t. And the condition of being a sweepout is that you have to start, say, t between 0 and 1. You have to start with the empty set and end with the whole manifold. Okay? And then, of course, for instance, one example is you choose your favorite Morse function, then you consider the level sets of that Morse function. So then, analogously, one can define the width of the Riemannian manifold as being the minimax number. And again, this number is easy to see that it's positive. And there's a theorem, the Minimax theorem, this was proven by, well, again, combined works, but Almgren, 65, Pitts, 81, and Shen Simon, also around 81. So what it says is that that number is the area of a minimal surface, but that minimal surface could be disconnected, and each component can come with some integer multiplicity. Okay, so the theorem says that any guy here, and in order to state it with smooth surfaces, one has to restrict the dimensions between 3 and 7. We're going to make a remark just after I finish the statement. So the theorem says that there exists a disjoint collection, say sigma 1, sigma q, of smooth, closed, embedded minimal hypersurfaces, and a collection of integers, positive integers, multiplicities, such that the width is the linear combination of the areas with these multiplicities. Okay, so this is this statement, and in particular, that implies that there's always at least one minimal hypersurface. Okay, always at least one. So let me make some remarks first. That in high dimensions, one can also do this thing, but if the ambient dimension is at least 8, then the minimal variety will be singular. And one can estimate the Hausdorff dimension of the singular set. In this case, it's going to be most n minus 7. And actually, what I'm going to maybe here for the purposes of this talk, I'll restrict to those dimensions, because some results hold in those dimensions we don't know yet about higher, and some results do hold in all dimensions. But let's stick with that case, because then we're sure that the surfaces will be smooth. And the second point, I always get this question, is that in dimension 2, this theory does not give closed geodesics. Okay, so if the ambient dimension is 2, then you can have point singularities, and the variety is actually it's going to be stationary for the length, but not necessarily smooth. So it's going to be a stationary network, or graph if you want. Okay, so let me say that, well, in 65, Almgren devised a very general minimax theory, and he was able to produce the existence of minimal varieties. But it was Pitts in the codimension 1 case who proved regularity by using the curvature estimates of Shen-Simon. Okay, and I should say here that this is really important, because I mean, I guess before the work of Shen, of course, very important to study area minimizers. But with Shen, people started looking at surfaces that are stable, meaning that the second variation of the area function is not negative, but maybe not globally area minimizers. And it turns out that the curvature estimates of Shen really play a fundamental role in the proof of regularity here, because the idea is that you prove regularity by approximating your variety by stable surfaces, not necessarily area minimizers, but stable. So you need to know the estimates for these surfaces. Okay, so that tells us that there is always one. And right about the same time, Yao conjectured that in dimension 3, contains infinitely many minimal surfaces. So from now on, when I say minimal hypersurface, I always mean closed and embedded. Okay. So the best result was this. There's the existence of at least one, and then with Andre, we started working on this problem a few years ago. And we adopted the point of view of that we have to look at cycles, but we actually thought at the time that the right way of looking at this problem would be to consider flat cycles modulo 2, and I will explain why modulo 2 gives you the right thing. So we decided to look at the space of cycles, so let me write the formal definition. So this is my notation. So this is just the space of n-dimensional flat cycles. And when I look at the connected component of the zero cycle, so every cycle is going to be a boundary, okay? Modulo 2 in M. So look at all, if you want all the space of all hypersurfaces, they might be unorientable. And the point is that by choosing coefficients modulo 2, the space of cycles turns out to be weakly homotopically equivalent to RP infinity. If you take integer coefficients and the manifold is oriented, by contrast, you get just a circle. Okay, so you get interesting topology by working with coefficients modulo 2. And there are sort of two ways of saying this. This actually follows from a formula proven by Almgren. So Almgren in 1960, I think it was a speech in the thesis, he proved the isomorphism theorem. What it says is that he computed the homotop groups of the space of cycles in great generality. So if I take the k-dimensional homotope group of the space of cycles, so L-dimensional cycles here in M, he proved that this is canonically isomorphic to the k plus L dimensional homology of M. Okay, this is his theorem. So in particular, if I take codimension 1, I will see that pi 1 of the space of cycles, this guy here, is Z mod 2, right? Because this is the top dimensional homology of M. And of course, I have nothing in high dimensions, so pi k, the space of cycles is 0 for every k greater than or equal to 2. And these are precisely the homotope groups of RP infinity. Okay, so it follows from this calculation. But we can also see this following way. This was an argument written in one of our recent papers. Well, you look at the other way of seeing these RP infinity structures by considering the boundary map. Which takes an n plus 1 dimensional chain. So just think of an n plus 1 is the top dimension. So an n plus 1 chain would be just, say, a region in M. So you can compute its boundary and get a cycle. Everything here mod 2. And then the point is that this is actually a 2-curver, right? Because if I have a cycle sigma, sigma is the boundary of some u, and the only other region whose boundary is equal to sigma is the complement of u. So this is a 2-curver. It's not difficult to see that the space of chains is contractible. So you can see that the boundary works like the projection from the infinite dimensional sphere to the infinite dimensional projective space. And then from that, you can compute pi 1 and pi k by lifting things to the contractible space. Okay, so the space is RP infinity. Of course, this is interesting because then we have multi-parameter sweepouts to work with. So we have RPKs for every k. So by exploiting this structure, we proved the following theorem. This was back in 2013. So we proved that for any closed Riemannian manifold, then either one has infinitely many minimal surfaces, minimal hypersurfaces, or one can actually find a disjoint collection of n plus 1 minimal hypersurfaces. So in particular, there are at least n plus 1 minimal hypersurfaces. And the corollary says that if we know that the Ricci curvature of G is positive, then it follows that two minimal hypersurfaces always intersect. So you cannot find a disjoint collection of such guys. So in particular, you have infinitely many. Okay. So this proves Yale's conjecture.
That's to make Schnirelmann theory geodesics when I get 3.
That's right. The number is a bit off by.
Yeah, it's not the same.
Yeah, we would get 2 here. That's right. But we do use ideas inspired by Lusten Schnirelmann theory. Yeah. Okay, so positive Ricci curvature implies infinitely many, and it's not really the positive curvature that helps. I mean, it's enough to know that there are no stable surfaces, because the idea is that if one has, if I have 2 disjoint minimal surfaces, say sigma 1 and sigma 2, they bound some region, then I can minimize, say, the area of sigma 1 in this region. Sigma 2 works as a barrier. And by minimizing the area in this region, I find sort of like a stable sigma bar stable minimal hypersurfaces. And that cannot happen in positive Ricci curvature because you see some negative direction in this orthogonal to the surface. So as long as one knows that there are no stable minimal hypersurfaces, one can get infinitely many, essentially. Okay. So how did we do this? How did we use the RP infinity structure? Well, it turns out that, again, this is inspired by Lutznig-Schnurman theory somehow. We looked at the cohomology of the space. So I want to define what it means to be a K sweep out inspired by this RPK sitting inside RP infinity. The right thing to do is to look at cohomology. So you take the one-dimensional cohomology of the space of cycles with coefficients mod 2. Well, this is an RP infinity, so this is going to be Z mod 2. So it has a non-trivial element, which I call lambda bar. So lambda bar is called the fundamental cohomology class. And turns out that this class has geometric meaning. The idea is that if you give me a loop of hypersurfaces, then the cohomology class lambda bar evaluated at that loop is going to be 1 if gamma is a sweep out and 0 otherwise. So how do you know it's a sweep out? Well, you have this loop of hypersurfaces, so if you want, you can keep track of the region that it bounds, and then as you go along the loop, when you come back, if the regions get interchanged, then it's a sweep out. Equivalently, if the lift to the space of chains is open, right? That's a sweep out, and then you get 1. If the family is trivial, you get 0. This is the fundamental cohomology class. And then, of course, again, I can compute HK of that space. And this is going to be also Z mod 2, and it's generated by lambda bar to the k, where lambda bar to the k is just the coproduct of lambda bar with itself k times. So I know the cohomology completely. And then I can define, I can use the following definition. So I will take X is going to denote a sequential complex. It's not fixed, could be anything. And then you say that definition, say that a map phi from that simplicial complex to the space of cycles is a K sweep out if, when I pull back lambda bar to the k, I get a non-trivial class in X. Okay, so if lambda defined to be the pullback of lambda bar satisfies lambda to the k, it's non-trivial in HK. So this is the definition. And then once you have the natural class of sweepouts, you can do Minimax. And then you can we define the following geometric invariant called the K-width. So let's say that if phi is a K sweepout, I'm going to denote it by phi belongs to P sub k. So the K-width is this number, which I denote by little omega k of mg. This is a minimax. I look at all k sweepouts note that the domain of a K-sweep-out is not fixed. It could be any simplicial complex. So for each K-sweep-out, I maximize over the domain of phi, of course, the area of phi of x. And then I minimize over all sweep-outs. So this collection of numbers forms what we call the volume spectrum of the manifold. So there are an increasing sequence of numbers. So we have omega 1, less or equal to omega k, and so on. And this notion somehow already, I should say, appears in the work of Gromov in the late 80s. So what Gromov was doing was he was thinking of hypersurfaces as zero sets of a function. Okay, so you parameterize the space of hypersurfaces by the space of functions. You just look at the zero set, and then of course, if I multiply my function by a non-zero real number, the zero set stays unchanged. So that is a infinite dimensional projective space. So in that particular setting, Gromov was interested in the notion of spectrum. If for a function you associate the Rayleigh functional, you get the standard spectrum for Laplacian, but maybe you can look at the area functional, you get somehow this notion. In particular, in 2003, I think he explicitly conjectured that this guy should obey a Weyl law. So I'm getting ahead of myself, but anyway, let me just say. Before going into that, let me just conclude what's the idea behind the Ricci curvature, or if you want, the without stable surfaces result, is that if there are no stable surfaces, then two minimal surfaces always have to intersect. So because the theory gives you an embedded surface, it has to have one component only, right? So this number omega k will have to be a single multiple of one component. You cannot have linear combinations. It's going to be a single multiple of one component. And somehow we argue that this contradicts the Gromov-Guth bounds, which I'm going to write here. So Gromov proved this before, and then Guth gave a different proof. So they proved that these numbers, omega k, they grow like k to the power 1 over n plus 1. With this constant C1 and C2 are constants that depend on the manifold, positive and depend on the manifold. So they grow sublinearly. Then the idea is that if you're getting a single multiple of one component, and if you assume by contradiction that there are only finitely many minimal surfaces, you should get linear growth. Okay, so this contradicts the sublinear growth of these numbers. So that's the idea behind our result. Okay, so at this point, of course, we wanted to prove that there are infinitely many. So at this point, we started working on the Morse index, and I will say more about it in a minute. But there's also this other approach that turns out that we were able to prove this conjecture. So let me write the statement. So this is proven with Evgeny Lyukumovich. I think he's here in the audience. I think this was 16. So we proved that there exists a dimensional constant A of n positive such that if I take the limit of the ratio between this number and k to this power, as k goes to infinity, this converges to A of n times the volume. Sorry? We still don't know the number. I was going to point that out, yeah. Yeah. I mean, it's possible to estimate it, but yeah, so as Peter pointed out, we don't know the constant. But of course, it's the same constant for all manifolds of.
Yes.
Well, it contains a phi, I'm sure.
Right, that, right. Right.
What kind of estimates do you have?
I don't know. I don't know by, my memory, but you can take, for instance, say you can choose your favorite manifold, like the sphere, and then you can work with polynomials, say spherical harmonics, and then you can bound the area by the degree.
So if you got a dimension 3, you have a procedure to approximate it to any accuracy 1, for example.
No, we don't have that yet. No. You can prove an estimate from above and from below.
But you can't improve it.
No, we can't prove it. Yeah.
You must be able to if you can prove it limiting exists.
Yeah. I mean, the proof of this starts with the cube. You prove it for the cube, and then somehow you go from the cube to Euclidean domains, prove that the same constants there, and then finally you go to Riemannian manifolds. But yeah, we don't need to know the constant. Of course, it's positive, right? Yeah. Okay. So this was the statement. And another remark is that, well, this holds in any dimension because it has nothing to do with regularity. And also works for manifolds with boundary, which is important, right? The cube has boundary. And then for manifolds with boundary, you have to consider relative cycles relative to the boundary. So an application that we found a year later application is a theorem we get with Erie, K. Erie, 117, I think. So we're able to prove that for generic metrics, so for a generic metric in the sense of bare, if you take the union of all minimal hypersurfaces, that union is dense in M. This is a density result. Later we proved some more quantitative statement with Song. But anyway, of course, this implies Yau's conjecture for generic metrics, but also proves more that at least for generic metrics, you know that given any small ball in the manifold, there's going to be a smooth surface crossing that guy. So let me just say what the argument is, because actually this is based on the perturbation idea of K. Erie applied in a different setting, but it turns out that it applies perfectly to our setting. We do need to know that each omega k is realized as the area of a minimal surface, and the only subtlety here is that omega k is defined through cohomology classes. So in particular, the domain is variable, so not homotop classes, you have to vary x. So in order to do that, there are some index estimates that I proved with Andre before, 15, I think. So we proved that that the index, if I sum the indices of the components, this is at most the dimension of the family. I mean, in this theorem, we allow multiplicities, but just we don't take multiplicities into account here. Okay, maybe it could be true even with multiplicities, but we do prove that the index of the support is bounded by k, which implies that each omega k is achieved as a minimal surface. So let me sketch the argument, a perturbation argument here, because it's really nice. So you might imagine that you have a metric, say some manifold here, and you might imagine that you only have, say, 4 minimal surfaces. So let's say 1, 2, 3, 4. So say these are the only minimal surfaces. Then what you do is you choose a point P outside those surfaces. Then you pick a small ball, disjoint from the surfaces. And in that small ball, you just perturb your metric slightly so that the volume goes up. Okay, find a one-parameter family of metrics, starting, of course, with the initial metric. And you bump the volume up. And then, of course, well, the volume of the metric G epsilon is strictly bigger than the volume of the original guy. So by the Weyl law, we know that some omega k will have to grow also, right? So we know that there exists some k such that omega k is strictly bigger than omega k of the original guy. But this is an invariant which varies continuously with the metric. And then the idea is that if somehow along this deformation, if you do not create minimal surfaces crossing that ball, then for every t in the family, omega k of that particular metric, it would have to be a linear combination of these guys with integer coefficients. So it would have to be constant, right? Because this is a discrete set. So the conclusion is that for some parameter t in the interval, say t prime, we create a new minimal surface, sigma prime, that intersects the neighborhood U. Okay, so you create somehow a new guy here. So you see that you went from 4 to 5, right? And then you can sort of like keep doing. Of course, this is not a completely rigorous argument, but you can make it work.
Properness for the minimal surfaces created here?
What's the question?
You have properness for the minimal surfaces you have here?
Properness?
Yeah.
I mean, they're all compact. Yeah.
So they are, okay.
Yeah, they're all compact. Yeah.
Yeah, so it's clear you need the Weyl law, not just the weaker value.
That's right. Yeah. So let me just point some questions from this. But before, I'd like also mention that these were generic metrics in relation with minimal surfaces were studied by Brian White, and he had proven that a generic metric is bumpy. Bumpy means that every minimal hypersurface is non-degenerate for the variational problem. So if you want, you can add that guy here because it's generic. Okay, so I think that it should be very interesting to study these surfaces. So I said that I was going to point out some problems. So basically, just some questions. We don't know anything about the topology of these guys. Okay, nor globally, not even locally. It should be very interesting to study, if you're in dimension 2, the genus of these guys, but in general, the Betti numbers of these things and how do they grow. How do they grow, maybe depending on the radius of the ball and things like that. We also don't know anything about the Morse index. You note that in this argument, I don't know which k is going to give me the strict inequality. I don't control k, so I don't have any information about the Morse index. It would be very interesting to study these guys. Also, one might hope to get density of individual surfaces. So this is saying that if I take the union of all of them, I get a dense set, but maybe there's a sequence of embedded guys which become denser and denser.
I mean, is that it? You believe that?
I think at least if there are no stable surfaces, I think that should be true. If there are stable surfaces, I'm not completely sure, but positive curvature, yeah.
It can't be something that might separate.
Yeah, well, yeah. I'm not completely certain what the answer is here. But definitely for this result, I mean, we don't get that. So,
Do you think there are results like, so I'm giving the ambient manifold, maybe I know something about curvature and so on, that I can bound the area of the minimal surfaces by an appropriate root of the volume of the ambient one. So for example, in symplectic geometry is a famous conjecture by Viterbo, which actually implies the so-called Mahler conjecture. If you have a convex energy surface in R to n, so you would as a Hamiltonian energy surface, then it surrounds some domain, and you take the nth root of that volume, and that should bound integral p dq, the action of the smallest periodic orbit on the boundary. And this Erie argument appeared before in symplectic geometry, so it's somewhat in this context.
Right.
So then I think maybe there are such kind of type of estimates.
yeah, there should be. You mean bounds with explicit constants?
Like
Yeah, right.
Constant
Right.
volume or something.
Yeah.
I mean, like you look at the round ball. You know?
Right. Yeah.
Does your proof give? It gives infinite many closed geodesics in even a lower bound, if I remember, but you don't know that there's some clever subsequence becoming dense, right?
No.
That's a strong
Yeah.
statement there.
Yeah. Okay, it's a question. Yeah. Yeah, okay. Also general metrics, right? I mean, whether is this a generic phenomenon or is it true for general metrics? We don't know. Okay, so there are lots of things to look at. So now let's like to talk about some other things one can do. So there's the question of what you can do for general metrics versus generic.
I take it back. I thought you were talking about the general thing. You were saying in the generic.
Yeah, this is generic. Yeah, generic. Yeah,
How much?
yeah, generic.
You're always cheaper.
Right. Yeah. Yeah. So general versus generic. So for general metrics, you're actually very happy that there is a result. My student Antoine Song recently this year, who solves Yau's conjecture. So let me state the theorem. So here he's in this range. Actually, we are also in this range, okay? So he basically proves that any guy contains infinitely many minimal hypersurfaces. So of course this implies Yau's conjecture. So let me say a few words about his proof, and then I'll go back to the generic case. So what Antoine did was, well, in our work, the problem was always caused by stable surfaces. Somehow, the stable surfaces hide what's happening inside, and so what Antoine says that, well, from our work, one can assume that there are stable surfaces. So he knows that there has to be some stable surface, and then he starts cutting the manifold along these guys until he finds some region here, some core, which is somehow the smallest region bounded by stable surfaces. And then inside that region, he has Frankel's property. So any two minimal surfaces here have to intersect. But of course, he cannot work with this region, because otherwise he would be producing minimal surfaces with boundary. So his insight is that one can consider the cylindrical extension. Okay. So he defines this omega hat, which is omega union the product of the boundary with 0 infinity. This is a non-smooth metric, but anyway, we can, it's a continuous metric if you want. And consider the volume spectrum of that guy, of the cylindrical extension, omega k.
Just jump right, where are you going to produce your infinitely many? Not in the
Inside here.
inside there.
Yeah, inside here. Yeah. Yeah.
Where's he going to? I should have skipped.
Yeah, you should, he's there. So this is a non-compact manifold, but you can define the volume spectrum by taking an exhaustion and computing the limit. And the point is that here, this spectrum does not grow sublinearly. It actually grows linearly. But he's able to detect the coefficient of the linear guy. So he proves that S grows at most k times the area of the largest boundary component, and then plus some constantized sublinear thing. So he's able to pick the coefficient here, the linear coefficient in the expansion. He's also able to prove that this bound holds from below. And then he can run sort of like a similar counting argument and actually find
Delocalizes at the very end.
infinitely many inside here.
It looks like you might be producing things in the cylinder.
That's right, yeah, yes. So the cylinder has a foliation by minimal surfaces. So sort of somehow the idea is that, you know, if you had like a minimal surface going inside the cylinder, it had to be like a leaf, because you can apply maximum principle. If you bring the sphere until it touches for the first time, you have two touching minimal surfaces, they would have to coincide. So we would have to, somehow the surface would have to disconnect and become like a leaf, and he rules that out. Okay. So in the end, he's producing infinitely many guys inside the core. Okay, so that's Song's argument. And to finish, I'd like to go back to the generic case. Some conjectures there. Okay, so going back to the generic case. So we have a conjecture. We call it the Morse index conjecture. So what we think is true is that generically, for a generic metric, there should be, well, first, the omega k has to be achieved with multiplicity 1. So it's going to be 1 times the area of a minimal surface. The surface could have many components, but each with multiplicity 1. And secondly, the Morse index of that surface should be exactly equal to k. I mean, this is not going to be true for general metrics, okay? Multiplicity 1. Not going to be true for general metrics. So what we proved recently, 18, was that 1 implies 2. Okay, so if I assume that it's achieved with multiplicity 1, then one gets the Morse index information. But I would like to finish with recent progress on that conjecture in dimension 3. And that uses the so-called Alencon variant. And the idea here is somehow to approximate the problem. So let me just say what it is. You take a potential which looks like a W could be this guy here. Then you have a parameter epsilon, and you have an energy which looks like this. I think it's this. So then you look at critical points of this guy, you get some other Lagrange equation, which I think looks like this. And the idea is somehow that if you look at critical points of these guys, as epsilon goes to 0, the level sets of these functions will concentrate at minimal hypersurfaces. I mean, this kind of thing goes back to the Georgi, but it's the connection with the construction of minimal surfaces is pretty recent. So let me just state a few results. So it's a theorem of Marco Guaracco, who I think somehow is also here in the audience, that if you have bounded energy and bounded index, and here I'm talking about solutions U sub epsilon of this equation, then the level sets of a subsequence will accumulate at a minimal hypersurface. So the idea is that these functions, there are two trivial critical points, -1 and 1. So the function tends to want to be constant, equal to 1 or to -1. So it happens that there's like a fight, and then it's going to be +1 in the end. It's going to be +1 in some component, -1 in the other component, and the interface will be a minimal hypersurface. So then Guaracco and Gaspar went on to get an existence theory using multi-parameter sweepouts. I think this is 15, maybe 16 here. And finally, I would like to mention work by Chodos and Mantoulides. Maybe Chodos is here too. In 18, and they prove basically that the Morse index conjecture is true in dimension 3. So they actually proved it for the Alenkah variant. So the omega k's that they have there are slightly different. It's coming from Gaspar Guaracco. But anyway, the advantage of using this approximation is that this function is actually Palais-Mail. I mean, it's very usual in geometry that we are always working in something that is borderline Palais-Mail. So you can get traditional existence theory for these guys. And of course, the problem is that you have a singular limit as epsilon goes to 0. But you do get an equation which helps. And with that equation, they are able to prove that the multiplicity is 1. And with the multiplicity 1 information, they get also the Morse index. So just like to point out that, of course, we'd like the conjecture to be true in all dimensions. Certainly up to 7. And in high dimensions also should be very interesting. I mean, how can we come up with a good definition of what the Morse index of a singular guy should be? I think that's a very, very interesting question. Okay, so you can see there are many open questions, and we hope to make progress during this year.
Thank you very much.
Thanks.